This lesson is going to focus on calculating equilibrium concentrations when we know the KEQ value. Let's look at an example of an equilibrium situation where we are asked to calculate the equilibrium concentrations of all species in our particular reaction. And we notice that they'll give a temperature. They always do. We don't really pay attention to that when we're doing calculations. And we notice that they give us the KEQ value. So we're going to have that. We can set up our expression, and then we'll be solving for an unknown in order to calculate all the equilibrium concentrations. So it says there that a mixture of 0.5 moles of hydrogen and 0.5 moles of iodine are placed in a 4-liter container. And these, again, are the initial concentrations. We have to be aware of that. So we always need to be mindful of what's initial, what is at equilibrium. And they're telling us nothing else. So we don't know any equilibrium concentrations. So the first step that we need to do is we need to calculate these initial concentrations of hydrogen, because we notice that the unit is moles and we need moles per liter. Now, the good news is that both of them are the same. So we're just going to kind of put this together. So the initial concentration of hydrogen equals the initial concentration of iodine, which equals moles divided by my volume in liters. So we're going to sub in 0.500 mole. We're going to divide by 4 liters. And we're going to get an initial concentration of 0.125 molar. And we'll worry about significant figures towards the end of the question. Okay, once we have that done, we now know we're going to need an ice chart because we have initial concentrations and they are asking us to solve for equilibrium concentrations. So we rewrite our equation, and I don't usually worry about states because right now we are studying equilibrium that is all gases. So we're going to set up my ice chart. So we have our initial, our change, our equilibrium concentrations, and we're going to sub them in. Okay, so we know that these initial concentrations here are 0.125 molar for hydrogen, the same for iodine, 0.125 molar. And we assume right now that that has been placed in the flask, the lid went on, and now we're waiting for the reaction to occur. So initially we have no product. Over time, those reactant molecules are going to collide, they're going to make products, and as a result, their concentration are going to decrease over time. And it'll be the same. It's a 1-to-1 ratio for hydrogen and iodine, but that HI concentration is going to increase, put a little plus sign there, by 2x, so twice the amount because of those molar coefficients. So at equilibrium, I end up with 0.125 minus x for hydrogen, the same, so 0.125 minus x for iodine, and then I end up with 2x for my product, my HI. Step 3 is to set up our KEQ expression. So we know that KEQ equals the concentration of my products, so concentration of HI raised to whatever power the coefficient that is present, divided by my reactants. And each of those have a coefficient of 1, so I don't see any powers there. Remember that this expression can only use equilibrium values. So what we're going to do is sub everything in that last line into the expression. So we have 54.3 as my KEQ value, and then HI at equilibrium is equal to 2x, and then I square that. And then I'm going to divide by 0.125 minus x for hydrogen, and then it would be times 0.125 minus x for iodine. Now, when I notice that I have two terms in the denominator here that are exactly the same, and I notice that I have a squared term right there, I'm going to do everything I can to make my life a little bit easier. So just follow with me over here. we're going to take that 54.3 value and we're going to equate that to, again, 2x squared. And then I'm going to group the denominator for 0.125 minus x, and I'm going to square that term. And when I do that, now I can take the square root of both sides. So let's do that. We're going to take the square root of the KEQ, and we're going to take the square root of my product and reactant side. So when I take the square root of 54.3, I end up with a value of 7.36, we'll say 89, round that. And then I end up with 2x divided by 0.125 minus x. Now what I can do is group my x terms and my non-x terms. So we're going to take everything in the denominator and we're going to cross multiply it across. So when we take 7.3689 and multiply it by 0.125, I end up with 0.9211 minus 7.3689x equaling 2x. So I'm just going to, again, group these. So 0.9211 equals 2x plus 7.3689x. And then if I group those together, okay, I end up with 9.3659x equaling 0.9211. And then my x term equals 0.098. So I am now going to round to 2 sig figs because back up here, this is what I had as the fewest number of sig figs when I initially calculated that molar concentration. So all I know now is x. I have to calculate still the equilibrium concentrations of everybody. So step 4 would be to do that. And so when I go over here to my equilibrium line, I notice that my hydrogen and my iodine are equal. So we can group those together. So concentration of hydrogen at equilibrium equals the concentration of iodine at equilibrium, which equals 0.125 minus x. So we'll sub it in, so 0.098. And when I subtract those off, I have to maintain fewest number of decimal places, which is 3, and I get a value of 0.027 molar. For HI was equal to 2x. So we're going to multiply 0.098 times 2. And when I do that, I'm multiplying. I have to maintain fewest number of significant figures. So I end up with an equilibrium concentration of 0.20 molar.